So we call these particles subatomic particles. Sub meaning below, atomic, they are below atomic size. These are the particles that make up the atoms. There are other subatomic particles, but in general chemistry, we don't need to care about them. The particle physicists care about them a great deal, but that's not what we're doing. So these are the three important subatomic particles: protons, neutrons, and electrons. The protons and the neutrons have essentially identical masses. They differ in the fourth significant digit here, 1.672 versus 1.674 times 10 to the minus 27 kilograms. Very small. Mass of the electron, 9.1 times 10 to the minus 31 kilograms. So it's almost 2,000 times smaller than a proton or a neutron. And so for a lot of purposes, we can just consider it to not have any mass because it's so much smaller than the protons and the neutrons. Kilogram is not a great unit for expressing the mass of these particles because it's way too big, right? So we created a unit. We made up a unit. We're like, well, that seems a little flippant. Well, if you think about it, all units are made up, aren't they? Some of them we're just more familiar with, and they seem like they've always been around. We can create units to be useful. So the atomic mass unit is a unit that is useful for expressing the masses of small particles. A lot of our units are named after scientists or something. This one has kind of a boring name, but it's very descriptive. It's the atomic mass unit, the AMU. It's not an AMU, which would be a relative of an EMU. It's an AMU. So the definition seems weird, but there's a reason for it. One atomic mass unit is 1/12 the mass of a carbon atom that contains 6 protons and 6 neutrons. So if we have 6 protons and 6 neutrons, that means we have 12 massive particles in the atom, right? And if we take 12 particles and divide by 12, we get 1. So what this means is that each proton and neutron weighs approximately 1 atomic mass unit, and that's why it was defined that way. So important things to know here. Let's see, I gotta choose a color. You should know the relative charges of protons, neutrons, and electrons. You should know the relative atomic mass. And so, actually, let me get rid of that. This is essentially 1, and essentially 1, and essentially 0. It's so small, it just doesn't really matter. And you should, of course, know their names. This table might be useful doing homework or lab problems where you need the mass of these particles in kilograms, and here's the charge in coulombs. We're not going to do much with a coulomb, it's just a unit of electrical charge. The relative charges here are what's important. So the number of protons is really important. That's what gives an atom its identity as belonging to a particular element. The number of protons defines the element. So we call that the atomic number. And the atomic number is given the symbol Z. I don't know why. I would have given it A, but they gave it Z. The atomic number is Z. It's the number of protons in the nucleus. So if we look at a helium atom, so here's a party balloon full of helium, and in the helium atom we have in the nucleus 2 protons. This atomic number is on the periodic table. If you look at the periodic table, each of those boxes has one whole number in it. That's the atomic number, the number of protons. If you find helium in the upper right corner, it's number 2. 2 protons. this illustration here, we're looking at the graphite and the pencil. Pencil lead is not lead. I had a class that didn't recognize that. You might think it was lead because they call it lead, but it's actually carbon. It's graphite, and so you can't get lead poisoning from pencil lead. That's good to know. In the carbon nucleus, there are 6 protons. Carbon's element number 6 tells us the number of protons. Oh, look, there's a periodic table. So here we have the atomic number and the chemical symbol of the elements. And then some periodic tables have the names, but the ones you have during an exam will not have the names. But in the periodic table, we have all the elements arranged by atomic number. Each element has a unique atomic number. It also has a unique chemical symbol. It's either 1 or 2 letters, and it's listed below the atomic number on the periodic table. So helium has the symbol He, carbon is a C, nitrogen, that shouldn't be capitalized, is an N. The first letter is always capitalized. The second letter, if there is one, is never capitalized. And we have to be very, very particular about that. You should have encountered element names and symbols in your previous chemistry class, whichever prerequisite you took for this class. I am going to expect that you know most of the element names and symbols. And if you want to know more particularly which ones, I'll let you know. So isotopes. It is true that all atoms of a given element have the same number of protons. They don't necessarily have the same number of neutrons. All neon atoms have 10 protons, but some of them have 10 neutrons, some of them have 11 neutrons, and some of them have 12 neutrons. So there's 3 different kinds of neon atoms, and each of them is going to have a slightly different mass. And the name we have for these atoms that are slightly different is isotopes. Same number of protons, different number of neutrons. The relative number of each different isotope in a naturally occurring sample of a given element is roughly constant. So if you got a sample of neon from Fresno and you went to South Africa and isolated a sample of neon gas, the ratio, the relative percentages of each different isotope would be close. So it's relatively constant no matter where you get the sample from. And we call these natural abundances, the natural abundance of the isotopes. We've had advances in mass spectrometry that allow more accurate measurements. And we used to say the natural abundances were the same everywhere. Now we know that there are small but significant variations for many of the elements. So that's a small change from a few years ago. General chemistry does not change much. That's like one of the few things that changes a little bit. So we said that the number of protons was the mass number. No, the atomic number. The number of protons is the atomic number that had the symbol Z. We have the mass number is given the symbol A. Why not give that Z and call the atomic number A? Wouldn't that make more sense? It's like they're trying to be difficult. I don't know. I need to look that up, but I'll do that in my spare time, which means it won't happen for a very, very long time. Anyway, the mass number is the total of massive particles, the protons plus the neutrons. So it's going to be a whole number. And we have several different ways of identifying the different isotopes. This is one way. It's sometimes called a nuclear symbol. Here, X is representing the chemical symbol for the element. We put the mass number on top and the atomic number on the bottom. So those 3 isotopes of neon would be indicated like this. This one has a mass number of 20. And if we want to know the number of neutrons, this is stacked up. So we could subtract 20 minus 10 is 10. That one has 10 neutrons. This one has 11 neutrons. This one has 12 neutrons. That's one of the few things about this that does make sense. the number of protons is the same. Okay, any questions yet? Another way is to take either the symbol or the name and just follow it with a hyphen and the mass number. Because really, do we have to specify the number, the atomic number, the number of protons? We can figure that out from the periodic table if we need to. So this is another way that we indicate different isotopes. So different ways of indicating the three isotopes. They've all got the same number of protons, different number of neutrons, their mass number will be different, and these are the natural abundances. So neon 20 accounts for 90.48%. Most neon has a mass of roughly 20, but a little bit of it has a mass of 21 because it has an extra neutron, and close to 10% has 2 extra neutrons. So here's an example. Silicon is a major component of semiconductor chips. It has 3 naturally occurring isotopes, silicon 28, 29, and 30. Determine the numbers of protons, neutrons, and electrons in each isotope. So we've got Si 28, Si 29, Si 30. We'll just make a table. Protons. How many protons does silicon 28 have? 14. We look at the periodic table and see it's element 14. How about the other ones? They all are 14. Protons is like your personality. It's who you are. It never changes. Neutrons. So this is the mass number. Protons plus neutrons. So how many neutrons does silicon 28 have? 14. And 29? And 30. 16. How many electrons do these guys have? They each have 14. In a neutral atom, the number of protons and the number of electrons has to be equal because the charges need to add up to 0. So protons and neutrons in a neutral atom is equal. Okay, that sentence just kind of died. The number of protons and the number of electrons in a neutral atom have to be equal. But the number of electrons can change. I kind of think of as the protons as being who the atom is, and the electrons have more to do with what it looks like to other atoms. So think, your hairstyle, whether you have tattoos or not, what kind of clothes you wear. It's the outside, it's what the other atoms see. And so you can change the outside, but you can't change who you are. Protons never change. Electrons can come and go. So if we gain or lose electrons, then the balance between positives and negatives is messed up, and we get ions. Ions are charged atoms. Cations are positive, anions are negative. Did I tell you the joke about the 2 sodium atoms? 2 sodium atoms were walking down a busy street, and one ran into a light pole. He's like, oh man, I think I lost an electron. And the other sodium atom said, are you sure? And the first one said, yeah, I'm positive. Yeah. So this sodium is positive because he lost an electron. Sodium has how many protons? 11. Sodium has 11 protons, and the atom has 11 electrons. If we lose an electron and have 10 electrons, then we've got 11 positives and 10 negatives. And you add that up, and you get plus 1 charge. Okay, cations are positive. This is kind of basic stuff, but I like cats. I have positive feelings for cats. Negatively charged ions are called anions. They're not anions. They're not a relative of onions. They're anions. So they're negative. It would be things like fluoride On the charges here, chemists have a thing about the number 1. We don't write 1s unless we have to. So this isn't a 1 minus or a minus 1, it's just the minus. And we always write the positive sign. This is different from exponents in math. We want it to look different. We don't want it to look like sodium squared or something, and so we always put the positive sign in there. But again, we skip the 1s if we can. Any questions about those guys? This should be old hat.